Okay, can you guys hear me now? Okay, so I'm joining. I'm joining on the audio on my iPad, and so you might hear some tapping because I'm also writing on that iPad too. But it looks like the audio in the classroom is not working. So we'll go ahead and use this for now, and then and then hopefully I'll call IT to so hopefully we'll be able to fix that before next week. Okay, good. Okay, so what I was saying kind of earlier in the class was that my plan or the plan right now is for me to return your midterms by Monday. And so there was kind of an emergency that kind of had to be dealt with. And so the plan right now is to return the midterms on Monday. And so if you want to come to class on Monday, I should have the midterms ready for you by then. But for now, everyone was able to see their midterm scores on Canvas, and so it should be online. And so I forgot to kind of mention this before too, but if you remember, the grading policy that we have in this class is that we're going to have two midterm exams. So our next midterm exam is going to be right before Thanksgiving. And I kind of have this kind of weighting system where whichever midterm that you score higher on, I'm going to give that midterm more weight than the other midterm. Okay. And so if you didn't score, or if you didn't get the score that you wanted on the first midterm, just kind of rest assured that if you do well on the second midterm, then you'll be able to kind of make up the points. Okay. I've in the past I've kind of done kind of like a version of this kind of on an individual basis, but I thought I'd kind of extend that same thing to everyone. Okay. So for right now, I've put the midterm scores in the higher midterm category just because there's only one midterm so far. But just know that after the second midterm is complete, I'll go in and kind of swap the scores. If you do better on the second midterm, I'll put your higher score on that weight. Okay. Okay. Audio still okay for the Zoom people? You guys still hear me? Okay. Good. Okay. Any questions I can answer before we get started for today? Yeah.
So we're gonna have our second midterm before Thanksgiving. Right?
Yes. Yeah.
And then, so are you gonna explain the project that we have before?
Yes. Yeah. So the project we're gonna talk about probably next week, actually. So I'm getting that stuff ready this week. So yeah, either Monday or Wednesday of next week, we'll spend a bit of time talking. And then I'll let you guys form the groups for that as well. Yeah. Just kind of very quickly. So the idea behind the project is that I'm going to let you guys choose basically a kind of a more specialized topic in biomechanics, and then I want you guys to essentially kind of prepare a lesson for that. And so the final week of lectures that we have is going to be kind of all just final presentations. And so I want you guys to think of it as like teaching the class about your specific topic using a lot of the information and concepts that we've learned all the way up until that point. Yeah, but we'll talk more about it next week. Yeah. Mm-hmm. Okay. Any other questions before we get started for today? Okay. All right. So let's go ahead and get started with the lecture today. And so the topic for today and Monday will be muscle dynamics. Okay. So we've already talked about muscles before, and we talked about muscles kind of within the context of static biomechanics. But now that we're kind of moving into the realm of human motion, human dynamics, there's more about muscles that we can discuss in terms of their behavior. Okay, and so we're going to start with kind of a very brief review in terms of how a muscle is structured and how a muscle generates force, and then from there we'll kind of launch into kind of the new stuff. Okay. Okay. All right, so let me go ahead and draw a diagram for you. So this hopefully should be a diagram that that's familiar to you. Okay. All right, so in particular, we're going to draw a diagram of the protein filaments within a muscle. Okay. Okay. So this is what it looks like within one sarcomere inside a muscle, right? So these are the protein filaments that generate force. Okay. So this entire unit here, we call this a sarcomere. Okay. And the main actors at play here are this thin filament on the outside. So we call this the actin. Okay. And on the middle here, we have the thick filament, which we call the myosin. Okay. And so what we talked about before is that when a muscle wants to generate force, these myosin heads, all these little kind of tendrils that kind of come out, they latch onto the actin and kind of pull the actin in one direction. Okay. And whenever the myosin heads attach onto the actin, remember, we call this a cross bridge. Okay. And then what happens that after the actin is pulled, they're pulled towards each other. And so what I've shown here is only kind of just one half of an entire kind of sarcomere. And so on the other side, you'll have other, myosin heads, and they're attaching on this way too, right? Okay. And so when this muscle wants to generate force, these myosin heads will attach to the actin and pull it this way. Okay. Okay. Almost kind of like the analogy that I think we drew then was like kind of, you have a ton of people just kind of rowing a boat, right? And so that's almost kind of exactly what it looks like. Okay. Okay. And so that's important because, a lot of the raw amount of force that a muscle can generate really depends a lot on how many myosin heads can attach to the actin. Okay. So that's kind of the first consideration that we'll look at. Okay. And another factor that kind of determines how much force a muscle can generate is how well the cross bridges can form. Okay. Okay. Because what we'll talk about in a bit, when your muscles are in motion, right, and so it's kind of actively contracting, this process of forming cross bridge is actually a time-dependent process. It's not something that happens instantaneously. And so if you're kind of moving your muscles too quickly, if you're contracting too quickly, then not as many of these cross bridges can form, and that kind of puts a limit on how much force your muscle can generate. Okay. Okay. So that's going to be kind of a central theme of today is how much muscle a force can generate in different conditions and how this relates down to the protein filaments. Okay. All right. And so just a bit of stats. I think we might have mentioned this before. And so, the way your muscles are organized is in kind of different tiers of different structures. Okay. Oops. And so kind of the smallest kind of team or the smallest kind of unit of measurement within a muscle is called a sarcomere. Okay. Okay. And so in terms of size, these are about 3 microns long. Okay. So basically invisible to the naked eye. So you need a microscope to look at it. Okay. These sarcomeres then can be arranged end to end to form something called a myofibril. Okay. And so myofibril is about 10 centimeters long. So, you have quite a few sarcomeres linked up together. Okay. And so, of course, with 10 centimeters long, that's something that you can see, right? And so that's kind of one thread or kind of one fiber that you kind of see with the naked eye. Okay. And then from the myofibrils, we can kind of arrange them in parallel. So we can kind of stack them kind of all together, or bundle them all together in one. And we call that the muscle fibers or myocyte. Okay. And so kind of the denomination kind of goes like this. And so, from a microscopic scale, here we have kind of a sarcomere. Okay. Where if you look inside a sarcomere, you see all the actin and myosin filaments, but I can't draw that small, so we'll just draw it as a rectangle. Okay. And then if you take these sarcomeres and you kind of link them kind of end to end like this, okay, you do this a few thousand times, a few kind of hundreds thousand times. This is a myofibril. Okay. Let me put some dots here just to indicate that it's still continuing, and so I can't link enough of those to kind of fit on the screen. But think of a myofibril as sarcomeres kind of linked end to end. Okay. And then inside a muscle fiber, okay, so let me kind of draw a muscle fiber as kind of a big cylinder like this. Okay. Inside this muscle fiber, we have a bunch of myofibrils arranged in parallel. Okay. And so in parallel means that they're kind of all kind of standing next to each other. And so that muscle fiber is kind of what you can look at, or it's kind of that's kind of the easiest thing to spot, when you're looking at a muscle. Okay. And then each kind of individual thread that you see within a muscle fiber, those are called the myofibrils. Okay. Okay. So that last bit was just some trivia. So I think, and so I only mentioned that just because there's a homework problem on it. Yeah, and it's that homework problem is it's not hard, and it's not anything that's you know, I would say it's not super important for what we want to do, but it's fun to kind of look at the sheer scale in terms of, you know, how many muscle fibers and how many myofibrils, how many sarcomeres that you have in kind of a typical muscle. Because you know, talking about it in terms of its length right here, you know, you can kind of see it, but you don't really get a sense of it unless you actually look at the raw numbers, which is kind of what that homework problem. So, okay. But for the grand scheme of things, what we're looking at, this is mostly just trivia. Okay. All right. Any questions on this? Okay. All right. So let's so that was just mostly review. So that's just kind of how a muscle works from the filaments. Let's get into some new stuff. So first, let's talk about relationships between force and length in the muscle. Okay. All right, and so the whole idea with force-length relationships is that the maximum amount of force that a muscle can produce depends on its length, on its kind of immediate length. Because if you look at a typical muscle, you know, because of the role a muscle plays in kind of human motion, right? Your muscle can actually go through a range of different lengths, and so you know it's not exactly kind of a static object. Because as your muscle contracts, you know, your entire muscle actually tends to shorten, and then when your muscle relaxes, you know, it lengthens, you know, quite a bit. So actually, if you look at an individual muscle, and so, you know, let's say that you look at your biceps, right? I think that's the easiest muscle to look at, right? If you kind of watch your muscle as you kind of go through the different motions, your bicep muscle itself kind of goes through quite a few different. It kind of varies in length quite a bit. Okay. Okay. We didn't really talk about this with human static because you know, in statics, you know, your muscle is kind of at a fixed length, and so it's kind of a moot point. But you know, when you're going through motion, right, then your muscles are going to change length, and then as the muscle changes length, it's going to produce, or it's going to be able to produce, a different amount of force. Okay. All right. And so the reason for this has to do with its with how the sarcomeres are structured in terms of the actin and myosin filaments. Okay. And so, you know, one way that we can kind of describe it is that this is due to the change in how many myosin heads can participate in a power stroke, okay, at a given length. Okay. So let me draw a couple pictures for you, and then we'll kind of talk about, we'll summarize it in kind of a kind of one figure at the end. Okay. So let's talk about kind of the best case scenario first. So the best case scenario is when your muscle can produce the maximum amount of force, okay? Okay, so your best case scenario is when your actin kind of, first of all, they don't overlap and, and they are as close together as possible, okay? And so we draw the myosin kind of in the middle. Okay. It looks something like this, and so. Why did I make this so long? Okay. Okay. You don't have to make it as long as me. I don't know why. I don't know why I did that. Okay. So this is the best case scenario because what you can see here, the way I drew this, is that every myosin head that's inside this sarcomere is engaged in the power stroke, right? So every myosin head is attached to the actin. Okay. And so when the nerve signal comes from your brain to contract, okay, so every myosin head will be able to participate in that. And so because you have every myosin head there, it's going to produce the maximum amount of force possible in that muscle. Okay. Okay. So that's the best case scenario. So you can almost think of that as kind of like the perfect length or the kind of the critical length of a muscle fiber. Okay. Okay, so let's look at situations for when your muscle is either too short or if it's too long. Okay. Okay. So both of these situations here will be kind of suboptimal situations. Okay, so let's go over the too short case first. Okay. And so one thing that's actually interesting about the actin is that they're actually kind of slightly offset from each other, or at least in terms of kind of how I drew here. And so when your muscle kind of contracts and your muscles get really short, the actin filaments actually start to overlap each other. Okay. And so it kind of looks something like this. Okay. And then your myosin is kind of in the middle like this. Okay. And so just like before, we can draw some myosin heads. Okay. Okay. And then let me actually extend this because the actin is actually kind of still in the middle right here. So you're going to have some heads out here that are not engaged with anything. Okay. So in this case, actin overlaps. Okay. And so when the actins overlaps each other, you kind of have, you can almost think of it like this. And so, the actin, the myosin likes to attach at certain locations on the actin, right? And so another way that you can think about this is that there are going to be some cross bridge sites on the actin that are not going to be utilized, okay? And then there's going to be some myosin heads that are also not going to be utilized, okay? And so this results in a lower amount of force. Okay. You have a similar effect that happens when the muscle is too long. And so when the muscle is too long, your actin are actually quite far from each other, like this. Okay. And so, it's a different extreme, but it kind of results in the same effect where, you have, myosin heads here, okay? But you have quite a few myosin heads that are not going to be engaged in the motion. Okay. So in this case, the actin's too far apart. So not all the heads are going to engage. Okay. And the same thing happens. And so this results in a lower amount of force. Okay. So this concept here about how the amount of force a muscle can generate depends on how much the filaments how they slide past each other. This is known as sliding filament theory. Okay. And so there's a lot of evidence that kind of suggests this, but as you can imagine, it's difficult to get kind of in we call it in vivo measurements, and so it's very hard to kind of put a microscope on someone's muscles and actually view it definitively as someone's moving. So you can set up some lab experiments to kind of model this, but at this point it's still technically a theory, although there is kind of a lot of evidence that supports this. A lot of it's kind of indirect evidence. Okay. Okay, and so we can sum this up using a curve, and so we call this the active force length curve. And so this active force length curve is kind of one of the most important things to that kind of characterize a muscle's behavior. Okay. All right, and so the idea is kind of like this. So on the horizontal axis here, we have the length, or the muscle length, or I should say sarcomere length to be more specific. And this is measured in microns, and so this is measured in micrometers. Okay. And then on the vertical axis, we're going to measure how much force the muscle can produce, and this kind of just has standard force measurements. So, for an individual so this particular graph here is for an individual sarcomere, and so the amount of force, of course, that individual sarcomere can produce is very minimal. And so for a lot of graphs, you see here that this muscle force doesn't have units, and so all they say that is that it's normalized. Okay. And so the curve kind of looks something like this. So if we start out at 1, this is like around 2, it's like around 3, 4, 5. Okay. And so the shortest a sarcomere can get is about 1.5 microns. So we kind of start the curve here, okay? And then it kind of comes up here. It reaches its plateau maybe around 2.75, okay? And then we kind of have a plateau region where we have kind of maximum force. And then at around 3.5, right around 3 actually. Right around 3, then the curve kind of starts to decrease until it hits about 5. Okay. Let me kind of emphasize that that the top there is kind of like a plateau. Okay. Okay, and so we can break this curve up into kind of 3 different sections. And so this is about this is called the ascending section. This is the descending section. And then the top here is the plateau. Okay. Okay. Actually, I kind of misdrew this a little bit. I had it in my notes here, but I just missed it. So the optimal sarcomere length. Okay. And so the optimal length of the sarcomere that you can produce the max amount of force. So thankfully there's a range, and so it's not just one value. It's around 2.2 to 2.7 microns. Okay. So it ends at right about 3. Okay. And then during the ascending portion, that's when the muscle fiber is too short. Okay. And you get kind of the actin kind of bunching up and overlapping each other, just like we said above. And then during the descending portion, the actin are too far apart, and you don't have all the myosin heads being engaged. Okay, so that's kind of explained the two every region there. Actually, let's leave that off. So it's implied by the. All right. Any questions on that? Okay. All right. So the active force length curve is something that's really important for muscles. Okay. And it's something that is actually very people like to optimize over this quite a bit. And so just as an example, there's a lot of research, just because there's a lot of money in it. There's a lot of research that goes into kind of the optimal forms for things like throwing a baseball or shooting a basketball, right? And so a lot of that has to do with this. And so when people talk about changing their form, of changing the way that they throw a ball or get into a stance or something like that, they're making use of this kind of research. Okay. All right. In addition to the active force length curve, we have something called the passive force length curve. Okay. And so the active force length curve has to do with the amount of force. Question?
For when you said optimal sarcomere length, did you mean the length when it's fully contracted at maximum force?
Exactly. Yeah. So if the optimal length, of course, when it contracts, it's going to shorten, but the optimal length is when it starts. And so when it starts the power stroke, that's the best length for it to.
So when it's producing.
Exactly.
When it stays in that position where it's producing the most force, the optimal length of the.
Yes. Yeah. Yeah. So that's right when the sarcomere starts the power stroke, that's the optimal length that it should have. Okay. So the active force length curve has to do with exactly that. So the muscle kind of actively producing force by expending energy and having the filaments kind of go through that. Okay. We've also talked about in the past about how muscles, they passively have some force generating capabilities as well, just from the fact that your muscle is an elastic solid, right? And so just like any elastic solid, if you take it and you stretch it beyond its resting length, there are some passive forces that get generated that can kind of help kind of return it to its natural length. Okay. So that's what this curve kind of represents. Okay. And so the passive force length curve looks something like this. Okay. And so we're again going to have the horizontal axis be sarcomere length. Okay. The vertical axis here will be some kind of normalized force. Okay. And then let me kind of put one thing here. So this little tick mark here will be 2.7 microns. Okay. And so up until that point, you know, your muscle isn't being stretched beyond its resting length, right? Because your muscle is actually quite compliant. And so it can actually be compressed and stretched quite a bit. And so you have to stretch quite a bit before, you know, you get any kind of force. And so up until 2.7 microns, you're going to see zero passive force. But then once you get beyond this, then the amount of force that gets generated actually goes up quite a bit, okay? Okay, but then once you kind of stretch a sarcomere beyond 2.7 microns, then that's when your passive elastic forces will kind of kick in and try to return the muscle to its resting length, okay? Okay. So, you know, we kind of talked about that quite a bit. So, you know, I'm not going to say much more about that. But then this kind of begs the question where, you know, both of these curves have to do with sarcomere length and the amount of force that sarcomere can produce, okay? And so if we kind of add these two together, right? And so because the amount of force that your muscle can generate is the sum of both its active and passive components, okay? We can get the total force length relationship. Okay? And for this, we're just going to simply add the curves. So we're going to add the passive and active curves. Okay. All right, and so for shorter lengths, the active curve is going to dominate, and so you're going to have something that looks like this. Okay, it's going to reach up to the plateau. You're going to have a little bit of a dip, and so there's a little bit of a dip associated with, you know, the fact that the active parts start to die away at longer lengths. Okay, because the myosin heads aren't able to engage, but then it picks up again, you know, later on. Because the passive components, you know, start to dominate at that time. Okay. All right, and so in this portion of the curve, this is the active forces. The active forces dominate. And then for this part of the curve right here, the passive forces will dominate. What's really interesting here is that, you know, if when you're looking at very high lengths or values of length for the sarcomere, you know, the passive components or the passive forces actually start to outstrip the active components. And so, you know, I think, you know, for most people, when you think about the amount of force your muscle can generate, you think about the active component mostly, right? So you think about, you know, how well trained you are and how much you can produce. But, you know, if you were to stretch your muscle to an extreme amount, you know, just the passive forces alone can be enough to kind of rival or even surpass the active forces. Okay, but keep in mind, you know, this only occurs when you stretch your muscles to kind of an extreme amount, and so, you know, don't go home and try this, because, you know, you might hurt yourself, and you know, I can't afford a lawsuit right now. Okay, any questions on force length relationships in muscles? Okay. All right, and so that's the relationship between force and length. Let's talk about force velocity relationships. Okay. And so during human motion, right, when your muscles are contracting, it's kind of continuously kind of changing length, right? And so as you go through a motion, and you kind of flex a muscle, it's you know, continuously changing, you know, to accommodate that motion. Okay. There's also a relationship in terms of, how quickly you contract and the amount of force that can be generated. Okay. And generally the relationship is the faster you're contracting, or the faster the muscle is moving, the less force that it can generate. And the reason for that is kind of the speed at which the cross bridges can form within the muscle. Okay. Okay. Because if you think of your muscle contractions as kind of myosin heads, attaching to actin, pulling it, detaching, relaxing, attaching again, and so that process takes time. And so if you're kind of doing a motion that requires your muscle to move too quickly, not enough of those myosin heads will be able to perform that, because there's some chemical reaction kind of things that are limiting it as well. Okay. And so we can summarize this in our force velocity curve. Let me draw it like this. Okay. And so on the horizontal axis here, we're going to have a contraction velocity. Okay. This vertical line that I drew here is for zero velocity. Okay. And so at zero velocity, so that's when your muscle is kind of maximally engaged, but it's not moving. So this is kind of like your static situation. Okay. And so this point right here is called the isometric maximum. So we call it we give it the symbol FOM. Okay. And so that's the maximum amount of force that the muscle can generate in a static situation. Okay. And so that's assuming that all the myosin heads are engaged and they're kind of pulling with all their might. Okay. And then as you get to faster velocities, and so to the right of this will be kind of faster speeds. This force here will kind of start to kind of tailor off like that. Okay. All right. And so the faster you move, the less force that that the muscle can generate. Okay. All right, but an interesting happens when you kind of get to the left of this curve. So to the left means a negative velocity. And so a negative velocity indicates that the muscle is trying to contract, but it's actually being pulled in the opposite direction. So it's trying to contract, but other forces are forcing it to elongate. Okay. And so if you kind of and so I think we went over that term before. So we call this eccentric contraction. Okay. Whereas on the right here we have concentric. Okay. And so during eccentric contraction, you actually have the opposite. So we have the force actually goes up. Okay. And so that term there for the isometric maximum is a little bit of a misnomer, because it's not actually the maximum amount of force that the muscle can generate, Because if the muscle is being elongated while trying to contract at the same time, it actually produces more force. And the reason for this is that on this left side of the curve here, in addition to the active components of the myosin and the actin kind of pulling together, we have some help from the passive components of the muscle as well. Okay. Okay. And so if you want to, if you're lifting something heavy, if you're lifting something heavy, you never almost do it very quickly, right? So you kind of have to like do it slowly so that your muscle kind of have a chance to kind of produce the force and produce the work that's needed to kind of lift something heavy. Okay. All right. Any questions on this? All right. So we'll revisit these curves. Probably not today, but probably on Monday. Okay. But for now, let's talk about muscle activation. Okay. So when I talk about muscle activation, this is, when a muscle is activated, that's when it receives a signal from the nervous system that it needs to undergo a power stroke, it needs to contract, okay? And so the way that this happens is that your nervous system, it starts from your brain. So your brain will send a signal down your spinal cord to each individual muscle. And then that little kind of electrical signal, electrical pulse, is what kind of initiates kind of the process of doing a power stroke, okay? Okay. And so upon receiving a signal, the muscle actually initiates a chemical process, right? And so the process of getting the muscle fibers to, or getting the myosin heads to attach into a power stroke requires actually quite a few chemical steps. Okay, so I'm just going to kind of mention them briefly here, but there's definitely a lot more biochemistry associated with this. Okay. Essentially what happens is that muscle cells will release calcium ions into the protein filaments, and that's basically kind of the catalyst which allows the myosin fibers or myosin heads to attach to the actin. Okay. And what's interesting is that this is very easily verifiable too. So what scientists have done is that they've actually attached electrodes onto the surface of someone's skin, and then as the person activates their muscles, those electrodes can actually sense those nervous signals. Okay, and so that's what's called an electromyography. Okay, and in fact, it's a very common diagnostic tool for people that are kind of experiencing issues with their muscles. To see if those nerve signals are getting there properly. Question? Yes.
Is that why they do the electrotherapy?
Yeah, and so electrotherapy is another area too, where you can kind of artificially stimulate a muscle by sending those electrical signals, instead of through the brain, but through kind of an external machine. And so I actually had that once because I was having some back issues, and so they attach some electrodes and they send some signals through, and it feels very strange. I did not like it at all, but some people really like it. Yeah, and then I think you've probably seen some devices and some products that claim that they can kind of work out your muscles when you're kind of sitting in the office, and they kind of work on the same principle where they send electrical signals to your muscle and try to get them to contract and engage without you actually having to do anything to. But those are kind of shady. So I wouldn't recommend those things. Yeah. Okay, so we can model this. So let me go through that kind of fairly quickly. And so we can use this using a time-dependent differential equation. Don't worry, it's it's going to be very brief. Okay. Because this process of so the process of sending an electrical signal to your muscles is actually very quick. It's almost instantaneous, just because electrical signals travel very, very fast. Kind of the rate limiting step here is actually this part. And so the release of the calcium ions into the muscle fibers, because this is instead of being an electrical process, this is more of a chemical process, and it takes it's still very fast. And so if you kind of try to observe it with the human eye, you may not really notice any difference, but these two things kind of work on very different time scales. Okay. And so the way we can model this is that we can have kind of two variables that model one, excitation. Okay. And so we can model excitation using a function u of t. And so this is kind of the electrical signal that comes from the nervous system. And then two, we have activation. So that's the muscle kind of actually responding to that nervous system signal and actually producing its power stroke. Okay. So we can label this A of T. Muscles engaging and power stroke. Okay. So those are our two variables, and we can kind of come up with a fairly simple differential equation to kind of model their relationship. Okay. And so the differential equation looks something like this. And so we have dA dt is equal to u of t minus a of t divided by tau. Okay. Where tau is a time constant, although it's not actually constant, it actually depends on time. Okay. So where tau equals, okay. So we have two cases for tau. And so on the one end, we have tau A, 0.5 plus 1.5 A of t. Okay. This is if u of t is greater than A of t. Okay. So this is kind of in the warm-up process. And so this is the part where the muscle is becoming activated. Okay. And so this is you can almost think of this as kind of the time constant that's the amount of time that it takes for calcium ions to fill the muscle fiber. Okay. And then, but what's interesting is that there's kind of a wind-up time for the calcium, and so it takes time for the calcium to fill the muscle fiber. There's also a cool-down time. So even when your brain tells your muscle to stop, there's actually a very brief period of time when your muscle actually stays engaged, because it takes some time to kind of flush out the calcium ions. Okay. And so that's what this different time constant is for. So this is tau d divided by 0.5 plus 1.5 A of t. Okay, and this is if A of t is greater than U of t. Okay. So this takes time. Okay. All right. So all that really says, and so we're not actually going to solve this differential equation. I just wanted to show you that there is a relationship. In the end, it kind of produces something like this. And so, if we model the excitation, so if we model the kind of the signal from the brain as a square wave, okay. So let's say that your brain is telling your muscle to activate over kind of that period of time. The actual activation of the muscle will actually look like this. And so, it's going to come up. Okay. Right. So it takes time for the muscle to activate, right? So the fact that, we don't go straight up to U of t is due to the fact that it takes time for the calcium ion to get there. Okay. And then when the excitation stops, it kind of takes some time for it to die down, just like that. Okay. And so in red here, we have A of t, which is the muscle activation. So you almost kind of have like a shark. I call kind of like a shark fin kind of relationship. All right. And so and let me just kind of emphasize that all of this happens very, very quickly. And so if you were to try to watch it, and so this period of time here. This period of time here, even though the way I've drawn it, it looks like kind of a long time. All of this takes place on the order of kind of microseconds. Okay, so it's not something that's actually observable, but scientists have kind of run tests and they've kind of gotten some test results that kind of verify this, that there is a little bit of a delay between the nervous signal and the chemical processes. And so this kind of very simple or fairly simple kind of mathematical model will capture that. Phenomenon. All right, any questions on this? Okay, so for the last 15 minutes today, I'm going to start the next section. It is a little bit long though, so we're probably not going to finish it today, but we'll continue talking about it on Monday. Okay, and so the next section here. So now that we've kind of talked about kind of the different relationships and the different factors that affect how much force a muscle can produce under different situations. Now is actually the time to start quantifying. Okay, so let's talk about actual muscle force production. Okay. So once a muscle activates, the raw amount of force, or I'd say the kind of the quantifiable amount of force it actually generates, depends on a lot of factors. Okay, and so it depends on the force-length relationship. It depends on kind of the speed of the contraction. But if you're talking about actually measurable force that the muscle can generate, it depends on the size and geometry of the muscle itself that you're looking at. because all that, all the information we've covered today is great, right? And so we've talked about how muscle force depends on sarcomere length, depends on shortening velocity of the sarcomere, but in kind of everyday use, that information is not that useful, right? And so what we're usually more interested in is how much muscle is my bicep able to produce? How much force is my my quadricep muscle able to produce? Okay, and so this next section is basically how do we take these curves and this data and this information that we have, and how do we actually apply that to real muscles for different people? Okay. Okay. And so another way you can kind of think of this is how do we take the information that we have, which is kind of normalized to kind of a single sarcomere, and how do we scale them for each kind of individual muscle for each individual person? Okay. Okay, and so the main factors that we're going to be talking about are mostly the size and shape of the muscles, as well as its orientation. Okay. And so there are 5 kind of defining characteristics of muscles that allow us to do this. Okay. So maybe do 1, maybe 2 today, and then and we'll go over the rest on Monday. Okay. And so the first characteristic that we'll talk about, it builds kind of directly on the force length relationships that we talked about today. Okay, and that's the optimal fiber length. Okay, and so the symbol we usually give for this is L0M. And so, we've already talked today about, for an individual sarcomere, it's the amount of the perfect length for a sarcomere to produce force is somewhere in the ballpark of 2.2 to 2.7 microns. Okay. But if you're talking about an entire muscle or an entire muscle fiber, a muscle fiber is comprised of, many sarcomeres that are linked in series with each other. Okay. And so the optimal fiber length here is actually the length of the muscle itself. Okay. The entire muscle fiber. Okay. And so that's kind of the operative word. So, I think, people kind of get confused between this and the sarcomere length, right? Remember that a muscle fiber is comprised of many sarcomeres. So, this is the length of the actual muscle that you can actually measure from the outside. Okay. Okay. So since muscle fibers are comprised of many sarcomeres, okay, right? So that's what your muscle fibers are essentially. And so the optimal fiber length is just going to be a multiple, right, of the of basically how many sarcomeres that you have in the muscle. Okay. Okay. And so the formula for optimal fiber length is quite well. And the calculations are quite simple. Just there's one term here that's very difficult to determine, but the formula is this: we have LOM is equal to N times LOS. Okay. For LOM, that's the parameter that we're looking for. LOS here is the optimal sarcomere length. Okay. And so this is, like we talked about, so 2.2 microns to about 2.7 microns. Okay. And then this N here corresponds to the number of sarcomeres in series within that muscle fiber. Okay. All right, so intuitively that makes sense, right? And so if you have 10 sarcomeres linked up together, then the optimal fiber length will just be 10 times that, because that's the overall length of the entire thing. Okay, but this has some kind of interesting consequences for our force length curve. Okay, because obviously in your body you have some muscles that are longer than others. Okay, so for longer muscles, longer muscles are obviously going to have a higher optimal fiber length. But what you're also going to see is that longer muscles also have a broader plateau region. Okay. And so the longer your muscle is, there's kind of a wider range of lengths that you can operate in and still produce kind of the maximum amount of force. Okay. Just because you have a lot more sarcomeres. Okay. And so if you use this formula up here and you literally you describe it as a range, right? And so you kind of have a lower bound, where the lower bound is you use 2.2 microns for LS. And then you have an upper bound where you use 2.7 microns. Okay. The higher your N, right? So let's say that your N, is very high, let's say 1 million, right? Then the difference between your lower and upper is going to be quite large. Okay. Okay. And so if you actually draw it out, it actually looks like this. And so for longer muscles, you have kind of two effects. Okay. You have a wider plateau region, and the plateau region kind of moves to the right. Okay. So for a short muscle, you may have something like this. Okay. So for a shorter muscle, you may not have as many sarcomeres that are lined up kind of end to end. And so your plateau region, it's kind of pushed to the left and it's fairly short. Okay. For a longer muscle, your optimal fiber length is going to be pushed to the right because you have more sarcomeres in total. And your plateau region is also going to be wider as well, because that difference between the upper bound and the lower bound also grows. And so, for a longer muscle, you might have something like this. right? So you have a wider plateau and it's kind of pushed to the right, okay? So this is the force length relationship. Okay. In particular, this is just active force length, okay? But the overall length of the muscle also has an effect on the force velocity relationship as well, okay? And so because longer muscles have more sarcomeres, there's a wider range of lengths that they can operate on. And so there's also going to be a wider range of speeds that it can operate on as well, okay? And so if we look at the force velocity curve, okay, for a longer muscle, you may have kind of a slower decay like this, okay? Okay. And then for a shorter muscle, it may decay faster, kind of like that, just because you don't have as many sarcomeres, and so you kind of get away from that kind of that sweet spot much more quickly. And so the overall length of your muscle has a big impact in terms of how it behaves under different scenarios. So not only the length, but also the force or the velocity as well. Okay. Any questions on this? Okay. All right. So that's all we got time for today, and so we'll close it off here. Okay. So next week will be kind of a busy week administratively because Monday I'm planning to return your midterms. And then we'll also talk about the final project next week as well. So definitely make sure you come for those. All right, so thank you guys for coming today. Hope you guys enjoy the rest of your day. Hope you guys enjoy your weekend, and I will see you guys next week. Yeah. Yep.
Sticking point for like the weight stack related to the sarcomere length?
It is. Yeah, it is. Yeah. So it's so there's kind of that just depending on the length of the muscle that changes the amount of force that can generate. So when you're doing a set, there's probably a region where you feel kind of much stronger than others. That's when you're at kind of that more optimal length. Yeah. Any final questions from Zoom before I close it up? Okay. All right. See you guys next week.